In this video, we are going to be discussing section A from the 2024 question papers. We're specifically talking about set 56S1, 2, and 3. So if you need any other specific questions, if you need any help, definitely let me know. Not just that, if you found this video helpful, do let me know. The reason I actually decided to, put this video out here is because under the sample question paper, I had the most views for section A. So I thought maybe, that's something you guys need. So as always, we're going to have the chapter name in the top over here, and then you'll also have the question and where to find the answer in the textbook. Also, we're going to, what I've done for this video specifically is that I've broken it down by chapter. So we're going to go about this video chapter wise, starting from solutions going all the way up to biomolecules. If you have any other specific question papers, definitely tell me, and I will also put the link in the description below as to where you can find these questions. I was actually able to find so many question papers in the CBSE website, and hopefully that is helpful to you as well. So just check out the link in the description below for that website. So the first chapter we're going to start with is obviously solutions. So the first question: for an electrolyte undergoing association in a solvent, the Van 't Hoff factor is. So obviously the fact that they've talked about the Van 't Hoff factor implies that it's from the last topic in your chapter solutions. So the Van 't Hoff factor came up because of them figuring out that the abnormal molar mass is the experimental molar mass, and the calculated colligative properties. All of these are assumed that the solute is neither undergoing association nor dissociation, but that's not the case. Even if you take sodium chloride, it's going to undergo dissociation, right, and water. So because of that, when it undergoes association, the Van 't Hoff factor I is less than unity, where for dissociation it is greater than unity. They've asked this specifically for association, so obviously the answer to this question, I'm going to take that. Okay, the answer to this question is going to be option D. It is always less than 1. Okay, the next question. So here, so you have these two questions, right? I actually found them from two different sets. So both of them had a version of the same question. So I thought we would discuss it together. So the first, so you have the assertion and reasoning. You are supposed to say if assertion and the reasoning are true, R is the correct explanation of A. Sometimes it's A and R, both these statements are correct, but R is not the correct explanation. That is, this does not completely explain the assertion. And then you have the third option where assertion is true and the reasoning is false, and then the opposite for option D. So here you have, when NaCl is added to water, a depression of freezing point is observed. So obviously when we talk about colligative properties, when you have a solute added to the solvent, there is an observation of what? Colligative property, which is depression and freezing point. That's the same case with elevation and boiling point as well. Both of these are observed because of them being colligative properties, and you have the solute added to the solvent. So the second reasoning, NaCl undergoes dissociation in water. Yes, it does. So the reason is true, but that doesn't actually explain the fact that the depression and freezing point is observed. Because of that, the answer is going to be option B for this. Okay, and here as well, you have elevation and boiling point is a colligative property. Yes, it is a colligative property, but that doesn't explain the fact that when NaCl is added to water, there is an elevation and boiling point that is observed. Because of this, this also is going to be option B. And obviously this, I couldn't like pick a specific thing from your textbooks. It's related to the overall concept of colligative properties in the chapter solutions. Okay, this one was a little difficult when I saw it first, but it's quite easy to solve. So phenol dimerizes in benzene having Van 't Hoff factor of 0.54. So we've been given the Van 't Hoff factor and we need to find the degree of association or the value of alpha. That's what we need to figure out. Okay, so first of all, when you have phenol, it has intermolecular hydrogen bonding. Okay, because of this intermolecular hydrogen bonding, you have a dimerization that is observed. So initially, the number of moles is going to be 1 for C6H5, that is the individual phenol, and then the dimerized form is going to be 0. After association, you have 1 minus alpha, which is alpha is the degree of association. Did I say dissociation? I meant association. And then alpha by 2, because you have two molecules being joined and forming, like it's forming a dimer. That's why it's alpha by 2. Now we know I is equal to the number of particles after association divided by the number of particles before association. So we have been given the value of I. Okay, so a number of particles after association is going to be 1 minus alpha plus alpha by 2, and before association is going to be 1. Okay, so we're just substituting these values and we are solving for a value of alpha, which is 0.92, and that is why you have the value 0.92. This is more conceptual. You need to understand this. The moment you figure this out and you can apply this equation, you should be good to go for this particular question. This is the next one. The system that forms maximum boiling azeotrope is. Now, this is under the concept of ideal and non-ideal solutions, specifically when we talk about non-ideal solutions. Non-ideal solutions are further classified into two: the ones which have a positive deviation from Raoult's law and the ones which have a negative deviation from Raoult's law. In case of a maximum boiling azeotrope, the ones that show a negative deviation from Raoult's law show form a maximum boiling azeotrope, and this makes sense, which is because the negative deviation is observed when you have the AA forces and BB forces that are weaker than AB forces. So your solution has a lot more intermolecular attractive forces, which in turn leads to an increase in boiling point. So obviously this will form a maximum boiling azeotrope. And out of this, we've been given the example of chloroform and acetone, and in your textbooks, which form negative deviation from Raoult's law because of hydrogen bonding. Because of this hydrogen bond that's observed, they will show negative deviation. Out of all of this, they show negative deviation from Raoult's law, and because they show a negative deviation from Raoult's law, they form maximum boiling azeotrope. All right, the next question is also related to the concept of the Raoult's law and the ideal and non-ideal solutions. You've been given delta H mix for an ideal solution is not equal to 0. Again, remember to read your questions properly, because I feel like I would have easily just missed the word not and just been like, oh yeah, the assertion is right. But that's not the case. AB interactions in an ideal solution are the same as AA and BB. And this is true for ideal solutions. And if that said the delta mix is equal to 0, maybe we could have picked option A. But the assertion is false because this is equal to 0. So answer is D. The assertion is false, but the reason is true. And the next question. We're done with the solution, the questions related to the chapter solutions. We're starting the ones with chemical kinetics. In the Arrhenius equation, when log K is plotted against 1 by D, a straight line is obtained. So this is basically related to the concept of the Arrhenius equation, where he explained the temperature dependence of a rate of chemical reaction. And actually this graph is given in your textbooks. Fun fact, I noticed that this question was in all the 3 question papers, like from the 3 sets of the 3 question papers, that is set A, B and C for this particular type. So according to this, when you have this equation, the slope is minus EA by R and the intercept is ln A. Now, if you remember it from your textbook, you would assume that I think it was minus EA by RT. You would assume one of these is right, but that's not the case, because the slope needs to be minus EA by 2.303 into R. Okay, so I think, yeah, 2.303 into R, because we're considering log K. So we're considering log K, so you'll obviously have to have 2.303, and the intercept is log A. And I know I haven't put any videos related to the chapter chemical kinetics. If you would require a specific concept, or you need a specific concept to understand, like need help with that, definitely let me know. The next question. For the reaction x plus 2y gives rise to P, the differential form equation of the rate law is, so you've been given all of this. Under the concept of rate law, I picked this example because this has most of the coefficients. If you notice that on the reactant side, you have minus 1 by the coefficient, and for the product side, you will have plus 1 divided by the coefficient. So based on that, for this particular equation that has been given to us, so the rate is going to be equal to minus 1 by actually 1, because there's no the coefficient is 1 for, so concentration of X divided by dt. Okay, then you have, this is going to be equal to minus 1 by 2, because that's the coefficient for Y. So 1 by 2 d concentration of Y by dt is equal to plus plus 1 by 1, because it doesn't have coefficient, d into concentration of P by dt. Okay, so now when you have this, you think, oh, this is the right answer. This is right. You're right. But basically, because it's been your options, all of them have interesting things in them. First of all, this minus dp, not possible because the product is always going to be positive. Here it's the same issue. In this case, you have 2 in the numerator. Because of that, this is going to be incorrect. So this is the only option that's right, because you can just remove this from the denominator and switch it to the numerator. So you'll have 2 d concentration of P by dt. So answer is option A. All right, the next one. Again, a reaction A2 plus B2 gives rise to 2AB occurs by following mechanism. So you've been given the first step, second, and the third step. So it occurs by 3 steps. What is the order of this reaction? So as we know, the rate of the reaction depends on what? It depends on, when you have multiple steps in a reaction, the rate is dependent on the slow step of the reaction. So the rate is going to be dependent on this particular step, and it involves only one of the reactants, so the order is going to be 1. Okay, so that's it. Simple. Just figure out which one is the slow step, and based on that, figure out the order of the reaction. The next question I have right here, because they're both quite almost related to the concept of order of the reaction. A zero order reaction is one whose rate is independent of what? When you think about a zero order reaction, we don't care about the presence or absence of light. Temperature of the reaction, no. Pressure, no. We care about the concentration of the reactant. The concentration of the reactant, the zero order reaction is the one where it is independent of the concentration of the reactants, which is why option B is the right answer. The next one is related to, we're moving on to the next chapter, D and F block elements. I think when I was in my 12th grade, I had to actually do the metallurgy, and I'm so glad you guys don't have to. I'm really glad. So the D and F block elements, which of the following first row transition elements is expected to have the highest third ionization enthalpy? So when we think about the third ionization enthalpy, we care about it. So when it moves from M to M plus, that is going to be the first ionization enthalpy. Okay, the second ionization is going to be M plus to M2 plus. Okay, so this transition is the second ionization enthalpy. M2 plus to M3 plus is going to be the third ionization enthalpy. That is what you need to remember. So when we're talking about the third ionization enthalpy, how easy it is for it to switch from M2 plus to M3 plus, that is what we care about. Okay, the one which doesn't want to do that is going to be the one which is going to have a very high third ionization enthalpy. And out of all of this, if you look at the electronic configuration, manganese Mn2 plus has a configuration of 3d5, and we know how they get about half-filled orbitals. When they have a half-filled orbitals, they don't want to let that go, and because of that, because of the fact that it's going to be difficult to remove that one electron from a half-filled orbital, that in turn implies that the third ionization enthalpy is going to be high for manganese. If you notice the others, for example, you have chromium, which is 3d4, that's fine. Iron, 3d6, it'll actually prefer if it got rid of that electron. And then you have vanadium, which is right here, which is 3d3, doesn't quite care. Because of the half-filled d orbital, you have the high third ionization enthalpy. Okay. The next question, the most stable oxidation state of iron is? Again, we can this is obviously even in your textbooks under the concepts of I think it was under the physical properties of uh, D block elements. But basically, when you have, we can just look at the electronic configuration. You have +2, +3, +4, and -2. We're not even going to bother with the -2. um, if you see +3, +2, and +4, you can obviously write it down here. But between all of these, 3d5 is obviously going to be the most stable, and that is for M3 plus, which is Fe3 plus. Because of that, this is going to be the most stable oxidation state of iron. The next question. This is again an assertion and reasoning question. Separation of zirconium and hafnium is difficult. Zirconium and hafnium have similar radii due to lanthanoid contraction. So obviously the answer to this question is A. First of all, zirconium and hafnium, it is difficult to separate them, and that is actually mentioned again in your textbooks under the concept of, I think, physical properties. So they have a difficulty in separation. Now this is because of a concept called lanthanoid contraction. The lanthanoid contraction makes sure that there is a similarity in radii between the third transition series, and this in turn leads to the fact that it is difficult because their atomic radii are closer or are similar. This in turn implies that it'll be difficult to separate them. Because of that, both assertion and the reasoning for this is correct. Next one was also, again, it's from a different question paper. Like it's from the same it's from a different set of the same question paper. I hope that makes sense. So separation of zirconium and hafnium is difficult. True. That is true. We just discussed that. That's because of the factor of lanthanoid contraction. The reason that they're given is zirconium and hafnium are radioactive, which is not the case. Like this does not explain the fact that it's the separation is difficult. Them being radioactive has nothing to do with the fact that it is difficult to separate them. Not just that, zirconium and hafnium are actually not radioactive, and because of that, you have assertion A is true, but the reasoning is false. The next is again an assertion and reasoning question. The assertion: transition metals have a high enthalpy of atomization. Reason: this is because transition metals have low melting points. Okay, transition metals cannot have low melting points. That is definitely not true. But they do have a high enthalpy of atomization, and because they have a high enthalpy of atomization, they have a very high boiling point. There is no mention of a weak or a low melting point. That's not possible. They're solids. Well, most of them are solids. So assertion A is true, but the reason is false. The next question, again related to DNF block: the equilibrium so and so exists in which medium? So this is under the concept of different oxides of the D block elements. So you have the ones where you learn about potassium dichromate, potassium permanganate. So this is because you have Cr2O7, it's obviously about dichromate. In the basic medium, if you notice, because of the presence of OH minus ions in the basic medium, this equilibrium exists. So we're just going to say, and this is directly based off what is in your textbook related to the potassium dichromate. We're done with DNF block. There were no questions related to coordination compounds. We're going to start with haloalkanes and haloarenes, our first organic chemistry chapter. Okay, so the compound which undergoes SN1 reaction most rapidly is. So SN1 reaction involves the formation, it involves two steps. The first step is the formation of a carbocation, and then the second step is when the nucleophile comes in, attacks from the back, and then that leads to the formation of our product. So the compound which undergoes SN1, for us to figure that out, we need to figure out the nature of our carbon atoms which is attached to the bromine atom. So this particular carbon atom is a secondary carbon, right? So this is a secondary alkyl halide. This one is a primary alkyl halide. This is, okay, I should probably write it down. Okay, never mind. Hang on. So this is the first one is a secondary alkyl halide. This one is a primary alkyl halide. This is also a secondary alkyl halide, and this is an arene, right? So Amongst all of these, we need to figure out which one undergoes SN1. So it's obviously not going to be B, because B tends to undergo, which is a primary alkyl halide, it tends to undergo SN2 reaction. So, and arene, it prefers to undergo an electrophilic substitution reaction. It does not undergo a nucleophilic substitution reaction. So this is obviously also out. So the answer in the end is going to be dependent on this and how stable our carbocation is. Between these two, because of the presence of a double bond, this carbocation is going to be basically it'll be this, right? So this can actually form resonance structures. Because of the ability of this particular carbocation to be stabilized because of resonance, this one tends to undergo SN1 more rapidly because of the fact that this carbocation is more stable. Okay, yeah, that's the answer to this question. The next question. Which of the following alkyl halides will undergo SN1 reaction most readily? So this is again under this SN1 and SN2 reactions. If you notice, all of these are groups given are the same. So it's CH3 taken thrice. They have missed the carbon, and because they missed the carbon, I'm pretty sure everybody who attempted this question actually got a mark. But if, let's say, hypothetically, they did add the carbon atom to this, so it would be CH3 thrice Ci. Okay, so this is what you need to have because they don't have the central carbon atom. Everybody was awarded a mark. When the R group is the same, you have the same order of reactivity in both mechanisms. So this, if you think about it, would actually undergo SN1 reaction because they are a tertiary carbon. Like the alkyl halide is a tertiary alkyl halide. So all of them will undergo SN1 reaction. And when it's iodine, it's more reactive, and then you have bromine, and then chlorine, and then fluorine. So based on this order, option A is going to be the right answer. The next question. Which of the following is more reactive towards nucleophilic substitution reaction? So amongst all of these, you have, again, it's quite similar to the first one that we discussed related to this chapter. You have arene. So obviously this is going to undergo electrophilic substitution reaction. This is a primary alkyl halide. This is also a primary alkyl halide, but it actually has a double bond here, and then you have here, which is again a primary alkyl halide. But out of all of this would probably be more reactive towards nucleophilic substitution because of the stabilizing effect of this double bond. And because of that, I'm going to have option D. Next one is we're moving on to the chapter alcohols, phenols, and ethers. The reaction of an alkyl halide with sodium alkoxide forming an ether is known as Williamson's synthesis. So it is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. So this is obviously under the preparation of ethers. And I also have a whole playlist dedicated to just discussing all the named reactions. So feel free to check it out. So it's just a straight, like, you need to remember what the name of the reaction is and mark the answer. So this is Williamson synthesis. The correct order of the ease of dehydration of the following alcohols by concentration of H2SO4. So we're using the concentrated H2SO4, so we're using the same reagent for dehydration. So dehydration is basically the loss of water molecule. So basically under the concept of dehydration in the chemical properties of alcohols, the relative order is tertiary, secondary, and primary. So we have to just pick. So this is a tertiary alcohol, this is secondary, and this is primary, and because of that, this is option A. This one, the order is slightly switched. Because of that, here you have a secondary, and then primary, and then the tertiary. So because of that, you have option A is the right one, basically. Dehydration of tertiary alcohol with Cu at 573 Kelvin gives what? Again, do not care about this dehydration. Dehydration means loss of water. Loss of water from alcohols leads to the formation of alkenes when it's a tertiary alcohol, and because of that, and that's reaction is actually given to you over here. It depends, right? Like, oh, I guess it did depend on the reagent depends for when you have copper, when you have a primary alcohol and a secondary alcohol, but in case of tertiary you just have the loss of water molecule leading to the formation of an alkene. The next question. Phenol on reaction with aqueous bromine at room temperature gives. So this is one of the reactions related to phenols, right? When it reacts, when it's treated with bromine water, it gives us 2,4,6 tribromophenol, which is formed as a white precipitate. So it's just a electrophilic substitution reaction. The next one. Phenol does not undergo nucleophilic substitution reaction easily due to what? So this actually, I thought this was actually discussed under the concept of ethers. So under the chemical reactions of ethers, this was what was given. So under this, if you notice over here, you have the phenol does not undergo cannot undergo nucleophilic substitution reaction. This is actually because of the partial double bond character between the carbon and the OH bond. Because of the COH bond being partially a double bond because of the benzene ring, you have that it does not undergo nucleophilic substitution reaction. The next one is aldehydes, ketones, and carboxylic acids. I feel like this chapter, even when I was studying, had so many chemical reactions. It was a lot. Anyways, so which of the following compounds will give a ketone on oxidation with chromic anhydride? So when you have secondary alcohols, they oxidize to ketones by chromic anhydride. So you have secondary alcohols, CrO3, chromic anhydride. So basically all you need to do is figure out which amongst all of this is a secondary alcohol, where this is a tertiary, this is a primary, so is this actually. So this is also, yeah, no, it's this carbon that we care about. This is not the carbon we care about. And then this is a secondary alcohol. So secondary alcohol undergoes this particular reaction. I just lost where I was. Okay, yeah. So this is actually under dehydration of alcohol. So you could either pick the chapter of, I think this is one of the common reaction ones. So this is actually, the reaction itself was from the alcohols, phenols, and ethers chapter, but this is one of the preparations of ketones. The next question. Acetic acid reacts with PCl5 to give what? So the reaction with PCl5, PCl3, and SOCl2 under the chemical reactions of acids, carboxylic acids. From there we know that the acetic acid, so you have CH3 COOH. So when you have CH3 COOH, so this is the R group is CH3, so you'll have CH3 COCl. So that's why the answer is option C, which gives us CH3 COCl, where CH3 is the R group, CO, and then Cl. Okay. Again, this is under the various chemical reactions related to carboxylic acids. The next question. The formation of cyanohydrin from an aldehyde is an example of a nucleophilic addition. Again, that is one of the, in the beginning for the various reactions of aldehydes and ketones, we've talked about various nucleophilic addition or elimination reactions. Out of that, addition of hydrogen cyanide is actually a nucleophilic addition reaction. The next one is an assertion and reasoning question. The pKa of ethanoic acid is lower than that of ClCH2COOH. The reason is chlorine shows electron withdrawing effect, which increases the acidic character of ClCH2COOH. The first thing we need to remember is the value of pKa. What does it tell us about the acidity? The higher the value, or let's say the lower the value of the pKa, the more acidic our compound is. So when you have hydrochloric acid, I'm pretty sure the pKa value of that is -7. So First of all, the assertion over here is that pKa of ethanoic acid is lower than that of this. So this means that ethanoic acid is a stronger acid than that of ClCH2COOH. Okay, but that is not the case. That is because chlorine actually shows the electron withdrawing effect, and because it shows this electron withdrawing effect, it's easy to form the carboxylate ion. So CH2COO minus is stabilized because this chlorine atom is pulling those electrons and in turn stabilizing this particular ion, right? So because of this, actually ClCH2COH is a stronger acid than that of ethanoic acid, and so because of this reason the assertion is false and the reason is true. And this is also given in your textbooks. You've been given the order of increasing acidity, so this is based on how well these groups are able to pull the electrons towards themselves, and you have also been given how strong the acidity is. So this is the least acidic and this is the most acidic. The reason I mentioned all of this is because the next question is also related to this concept. The pKa of NO2CH2COH is lower than that of CH3COOH, and this is true because the NO2 is an electron withdrawing group. It pulls the electrons towards itself, so it's going to be a stronger acid. It makes this a stronger acid than this, and if it's a stronger acid, the pKa value is less. Okay, and the reason given here is because it shows electron withdrawing effect, and this in turn increases the acidic strength. So because of that, both A and assertion and reasoning is true, and the reason is the right explanation of A. Again, with continuing with the strength of acids, I feel like it's really important to know these concepts. So assertion, fluoroacetic acid is stronger acid than chloroacetic acid. This is due to greater electron withdrawing nature of F than C, which is also true. First of all, the reason given over here is true. If you notice, F is a better electron withdrawing group than Cl for obvious reasons, more electronegative. And because of that, you will have that the fluoroacetic acid is stronger than chloroacetic acid. Because of that, again, A is the right answer. The next question, which of the following is the strongest acid? So we've been given these four, which I've written over here. So you have COOH and Cl, COOH, OH, just the COH, and then a COH and the NO2 group. Now, amongst all of these, chlorine and NO2, both of these are electron withdrawing in nature, and they will in turn help stabilize the benzene, like the carboxylate ion, which is formed. Okay, OH on the other hand is an electron releasing group, so it will not help the help stabilize the ion. This has no group, so we're going to ignore it for now. So the question is between Cl and NO2, which is a better electron withdrawing group. From this order, it's obvious that the NO2 is more electron withdrawing than Cl, and because of the nitrate group being more electron withdrawing, option D is the right answer. Okay, and again, this is also related to the concept of acidity of carboxylic acids. The next question. The product formed as a result of CH3MgBr and CO2 followed by hydrolysis is. So this is one of the methods of preparation of carboxylic acids from Grignard's reagent. If you notice, Grignard's reagent is almost, I think I'm pretty sure it's present in almost all your chapters. It is a very versatile reagent and it's used for multitude of different chemical reactions to give us different preparatory chemical reactions, if you will. So when you have RMgX, so you have CH3MgBr and CO2 in the presence of dry ether and hydrolysis. So this gives us RCOOH. So amongst all of these, this is an aldehyde, ketone. Both of these are out. So the answer is either this or this. And because we have an R group, which is CH3, right? So because of that, the answer is option D. Okay, it's just based on the methods of preparation. The next question. Decarboxylation of sodium benzoate on heating with soda lime gives. So decarboxylation reaction essentially means that the carboxylic acid is losing a carbon dioxide. Okay, and this in turn leads to the formation of hydrocarbons. So benzoic acid, no. Benzaldehyde, definitely not. Toluene, No, because you don't have an addition of a carbon group, and because of that, answer is option A, which is benzene. Essentially what's happening is you have this COONA, right? So this is getting removed and we are replacing it with a hydrogen. Because of that, you have the answer as benzene. The IUPAC name of this is what? So this actually 3-oxopentanal is one of the examples which is discussed in your textbook, which is why it is so important for you to, keep looking at all of these little things in your textbooks. And I know it's a lot. You have 4 subjects that you have to learn, and you have to make sure that you learn everything from all of them. And it is a lot, and I recognize that. But basically, this is going to be 3-oxobutanol. Oxo because of ketone, aldehyde aldehyde is the primary functional group, and then you have 1, 2, 3. So the third carbon has a CO group attached to it, which is a ketone. And then you have 4 carbon atoms making it bute. So the answer is going to be 3-oxobutanal. The next question. I feel like there are more questions related to the chapter aldehydes and ketones and carboxylic acids. So the product X obtained in the following reaction is, so AG, you have this particular thing where you have double bond O and then CHO. So this has a ketone group and an aldehyde group. You have Ag and H3 taken twice OH minus, which is basically the Tollens reagent. So ammonical silver nitrate solution over here. And we know between aldehydes and ketones, it's the aldehydes that undergo reaction. And because of that, it's the aldehyde group that is going to get converted to COO minus. It's not going to affect the ketone group, and it is going to form COO minus. And because of that, this is the answer. Again, this and this is wrong because it doesn't affect the ketone and doesn't form an alcohol. So this is obviously wrong. Which of the following has the highest boiling point? Now, when you have over here, what you have over here is CH3CHO, which is an aldehyde. This is acyl chloride. You have COCH3, which is a ketone. And then you have an acid. Amongst all of these, acids are known to have the higher boiling points compared to their aldehydic and ketonic of comparable molecular masses. That's what I wanted to say. So compared to that, you have the acids with the highest boiling points. This is because of the concept of hydrogen bonding. Okay, and this acyl chlorides obviously don't have the hydrogen bonding because they don't have the COOH group. The OH group is what is responsible for the hydrogen bonding. So this won't be the case. And compared to aldehydes and ketones, acids are obviously going to have a higher boiling point when you have a comparable molecular mass. And because of that, the answer is option D, because of intermolecular hydrogen bonds. And I hope at this point you know what inter and intramolecular hydrogen bonds are. If you do not, definitely let me know. The next question. The suitable Grignard reagent used for the synthesis of this with methanol is. So you have HCHO, and this alcohol is a primary alcohol, right? So between all of these, right, this particular one is what leads to the formation of a primary alcohol. So this is what we're going to use for the synthesis, and the R group is what we care about. So the R group is going to be just whatever is all of this is going to be the R group, and because of that, the answer is option C. Okay, do not get confused because you do have another carbon atom coming from methanol. Okay, so when I saw this question, I was immediately like, oh, this is the right answer because of the number of carbon atoms, but that's not the case because you have the HCHO. Because of that, you need to remember that this is the right answer. And of course, this is not the right one because this would have led to CH3CH2OH, which is ethanol. And this would have just given us methane, ethane, propane, butane, butanol. So because of that, answer is option C. The next one is the next questions are related to the chapter amines. So the first one is assertion and reasoning question. Aniline is a stronger base than ammonia. Yeah, right. The unshared pair of electrons on nitrogen in aniline becomes less available for protonation due to resonance. The value of pKb of aniline is actually quite high, and this obviously means that aniline is a weaker base compared to ammonia. We just discussed pKa value. It's similar. The concept is quite similar, where when you have a lower pKb value, it makes a stronger base. When you have a higher pKb value, it is a weaker base. So the pKb value of aniline is actually quite high, and that's because of this. So actually the reason is right. So if they just said aniline is a weaker base than ammonia, we would have hit option A. But the assertion is wrong, but the reasoning is true, and because of this, the answer is option D. The next question. Para-nitroaniline is a weaker base than para-toluene. The electron donating NO2 group in para-nitroaniline makes it a weaker base. So basically, when you have this, para-toluene is one of the things given in related to the IUPAC nomenclature in the chapter amines. Okay, so you have a para group NO2 over here, and then you have a CH3 group. Okay, so CH3 and NO2. CH3 group is electron releasing in nature, whereas NO2 is electron withdrawing, right? We know that by now. So when you have this, the para-nitroaniline is actually a weaker base because of the fact that it's pulling those electrons, and that in turn implies it'll make it a weaker base. So it is true, but the reason is wrong because they've mentioned that NO2 is electron donating. NO2 is not electron donating, and because of that, the assertion is true, but the reason is false. If they said the electron releasing withdrawing group, that is NO2, it would have been right. So they've mentioned it incorrectly, which is why it's wrong. All right. They just had two questions related to amines. That's interesting. Okay, the next questions are going to be related to the last chapter that we're going to discuss, which is biomolecules. And most of these questions were directly from your textbooks. The others you had to think a little bit. In this, it was just almost straight from your textbook. Two among the three components of DNA are beta D2 deoxyribose and a heterocyclic base. The third component is what? So when you think about it, adenine and uracil, both of these are actually those nitrogen bases. Sulfuric acid, not present in our DNA, isn't sulfuric acid present in our stomach? I think so. Or I could be wrong. It's been a long day. I think it's, oh no. Hang on. I need to look this up. Boy. Stomach acid. Oh, it is hydrochloric acid, not sulfuric. I am so sorry. So it is not present in our body. Sulfuric acid, not present in our body, should not be present in our body. So the answer is obviously going to be the phosphoric acid, and that's given in the chemical composition of nucleic acids. And where is it? And here, right here, phosphoric acid. Okay, because of that, answer is option B. The next question, which functional group of glucose interact to form cyclic hemiacetal leading to pyranol structure? So we obviously have the aldehyde group from the first carbon atom and the fifth carbon atom with the hydroxyl group, and that's what the answer is going to be. So aldehyde group and the hydroxyl group at C5. This leads to the hemiacetal structure. C4 is wrong, obviously, and then you don't have a ketone group over here. It's an aldehyde group, so that's why option C and D are wrong. The next one, nucleotides are composed of nucleotides. It consists of, where is it? Here. You have a base, the nitrogenous base. You have the sugar, which is the pentose sugar, and the phosphoric acid. All these three components together make the nucleotides. See, I told you, biomolecules is easy. You got this. Okay. Did I skip a question? The specific sequence in which amino acids are arranged in a protein is called as the primary structure. Basically, each and every amino acid is attached in a certain sequence, and this sequence is said to be the primary structure of that protein. So that structure, that arrangement is called as primary structure. Next one, maltose is made up of glucose and glucose. So the answer is going to be C. The remaining are obviously incorrect because they don't have the individual carbohydrates written correctly. The next question, all proteins on hydrolysis gives alpha amino acids. Enzymes, no, because big protein structures are enzymes. Glucose, definitely not. Polypeptide, probably not. So the answer is alpha amino acids, and only alpha amino acids are actually obtained on hydrolysis of proteins, and this is discussed under the concept of amino acids. Oh, with that, we're done with discussing all of these questions. Definitely let me know if you found this video helpful. That obviously is a huge boost to knowing what you want, um, and if you have a specific concept or anything that you need help with, definitely let me know about that as well. Not just that, check out the playlists or whatever videos are showing up right now. That obviously in turn helps my watch time, and that helps me know what you liked. With that, we're done with this video. And yeah, and check out the link in the description below where you can find out more of these CBSE question papers. And I'm sure there's where I'm sure you'll find that helpful. You got this. Wait, my mouse is missing.